Imagine a place where light itself cannot escape, where the very fabric of space and time bends so completely that even our most fundamental understanding of reality begins to break down. A place that exists not in the realm of fantasy or nightmare, but right here in our universe, scattered throughout the cosmos like invisible lighthouses marking the most extreme boundaries of physics itself. Hello and welcome to the Sleepy Astronomer. Tonight, we're venturing into one of the universe's most profound mysteries, black holes, those cosmic enigmas that have captured human imagination for centuries, long before we had any real understanding of what they might be. We're going to explore places where gravity becomes so intense that it overwhelms every other force in nature, creating pockets of darkness so complete they seem to swallow the very concept of existence itself. If you're settling in for the first time, welcome to our gentle journey through the cosmos. And if you've travelled with me before to distant planets and ancient stars, it's wonderful to have you back among the mysteries. Whether you're tucked into bed, curled up on your favourite chair, or perhaps lying back where you can see the stars through a window, I'm glad you're here for this particular adventure. Our journey begins not with the modern space telescopes that have revolutionized our understanding, but with an English clergyman named John Michell in 1783. Using nothing more than Newton's mathematics and his own profound intuition, Michell imagined what he called dark stars, massive objects so dense that even light could not escape their gravitational pull. He was describing black holes more than 2 centuries before we would actually find one, using only the elegant logic of mathematics to peer into the darkest corners of the universe. There's something deeply humbling about the fact that these objects, among the most invisible things in the cosmos, are also among the most influential. Black holes don't announce themselves with brilliant light or colourful gases. Instead, they reveal their presence through absence, the way they bend light around themselves, the way they pull on nearby stars, the way they seem to carve holes in the very fabric of space-time itself. Ancient cultures, gazing up at the night sky, told stories of cosmic serpents that devoured light, of wells of darkness that led to other worlds, of places where the ordinary rules simply didn't apply. They couldn't have known they were describing something that actually exists, scattered throughout our galaxy and beyond. Places where space curves back on itself, where time slows to a crawl, and where the matter that falls inward is stretched and compressed beyond recognition. Einstein himself was reluctant to believe in these objects, even though his own equations predicted their existence. God does not play dice, he famously said about quantum mechanics. But perhaps he might have added that God does play with the geometry of space-time itself, creating regions where our everyday experience of reality simply ceases to apply. Tonight we're going to follow the thread from those early mathematical musings to the extraordinary discoveries of recent years. We'll explore how these invisible monsters are born from the depths of the most massive stars, how they warp the space around them into impossible geometries, and how they challenge every assumption we might have about the nature of time, space, and information itself. We'll drift gently from the familiar realm of stellar evolution, stars living and dying according to the same nuclear physics that powers our sun, toward the edge of physics itself, where Einstein's gravity meets quantum mechanics in ways that still puzzle the brightest minds in science. Along the way, we'll discover that black holes aren't just cosmic vacuum cleaners, randomly devouring everything in their path, but elegant, almost living entities that seem to encode information about everything they've ever encountered. From the supermassive giants that anchor the centers of galaxies to the stellar mass black holes created in the final moments of massive stars. These objects shape the architecture of the universe in ways both subtle and profound. They're the universe's ultimate recyclers, taking matter and energy and processing them through the most extreme physics imaginable before releasing them back into the cosmos as pure energy. Perhaps most remarkably, we've recently learned that black holes themselves are mortal. Through a process so subtle it takes longer than the current age of the universe, they slowly evaporate, returning their contents to the cosmos in the form of radiation so faint it's almost impossible to detect. In their birth, life, and eventual death, black holes embody some of the deepest principles that govern our universe. So find your most comfortable position, whether you're nestled under blankets, settled in your favourite listening spot, or perhaps gazing out at the stars themselves. Take a slow, deep breath, and let's begin our gentle descent into the ultimate darkness. Out there, in the space between the stars, black holes wait in perfect silence, invisible sentinels marking the places where matter and energy have crossed the ultimate threshold, where the ordinary rules of physics give way to something far stranger and more beautiful than anything our everyday experience could have prepared us to imagine. To understand how black holes are born, we need to begin with something much more familiar: the gentle, steady light of the stars themselves. Every star you can see on a clear night is engaged in the same fundamental battle, a cosmic tug-of-war that has been playing out for billions of years. On one side stands gravity, always pulling inward, trying to collapse the star into the smallest possible space. On the other side stands the star's own nuclear fire, pushing outward with the energy of hydrogen atoms fusing into helium deep in the stellar core. For most of a star's life, this is a remarkably stable arrangement. The inward pull of gravity is perfectly balanced by the outward pressure of nuclear fusion, creating what astronomers call hydrostatic equilibrium. It's a delicate dance that can continue for millions or even billions of years, depending on the star's mass. Our own Sun has been performing this balancing act for about 4.6 billion years, and has roughly another 5 billion years to go before the music stops. But like all dances, this one must eventually end, and for the most massive stars, those born with more than about 20 or 30 times the mass of our Sun, the ending is both spectacular and profound. These stellar giants live fast and die young, burning through their nuclear fuel at such a furious rate that their entire lives span only a few million years. When their fuel begins to run low, the careful balance that has sustained them starts to falter. The process that leads to a black hole's birth is almost like watching a cosmic clock wind down, tick by tick, as the star approaches its final moments. In the core, hydrogen has long since been exhausted, fused into helium during the star's youth. But massive stars have a trick that smaller ones don't. They can continue burning heavier and heavier elements, each new fuel source requiring higher temperatures and pressures to ignite. First, helium begins fusing into carbon and oxygen, the core growing hotter and denser as gravity slowly gains the upper hand. Then carbon ignites, creating neon, sodium and magnesium, in a process that lasts only a few thousand years, a cosmic eye blink compared to the millions of years the star spent burning hydrogen. Neon burning follows, then oxygen, each stage shorter and more frantic than the last, like a candle burning down to its wick. The star's interior during these final stages resembles a set of nested spheres, each layer burning a different element. Hydrogen fusion continues in the outermost shell, while deeper layers burn helium, then carbon, then neon, like Russian dolls of nuclear fire. The temperatures at each level are almost incomprehensible. Millions, then tens of millions, then hundreds of millions of degrees. The pressures are so intense that matter behaves in ways we can barely imagine, with atomic nuclei stripped of their electrons and compressed into spaces smaller than individual atoms. But there's a limit to this process, a final wall that even these massive stars cannot break through. That wall is iron. When the core begins producing iron through silicon burning, the stellar clock strikes midnight. Iron is the most stable nucleus in the periodic table. It takes energy to fuse iron into heavier elements, rather than releasing energy. For the first time in the star's life, nuclear fusion becomes an energy sink rather than an energy source. The moment iron begins to accumulate in the core, the star has perhaps hours, maybe days, before catastrophe strikes. The core, no longer supported by the outward pressure of energy-producing fusion, begins to collapse under its own gravity, and when it collapses, it does so with a violence that defies easy description. In less than a second, faster than you can blink, the iron core shrinks from something the size of Earth to something smaller than Manhattan. The matter becomes so dense that atomic nuclei are crushed together. Electrons are forced to combine with protons to form neutrons, and the very atoms that make up ordinary matter cease to exist. The core becomes a single, giant atomic nucleus, held up not by electromagnetic forces between atoms, but by the quantum mechanical pressure that prevents neutrons from occupying the same space. This is where the story can take two different paths, depending on just how massive the original star was. If the core is below a critical mass, about 2 to 3 times the mass of our Sun, neutron pressure can halt the collapse. The core rebounds like a cosmic basketball, sending a shock wave outward that tears the star apart in what we call a core collapse supernova. What remains is a neutron star, a city-sized object so dense that a teaspoon of its material would weigh as much as Mount Everest. But if the core is more massive than this critical threshold, a limit discovered by physicists Robert Tolman, J. Robert Oppenheimer, and George Volkoff in the 1930s, not even neutron degeneracy pressure can stop the collapse. At this point, no known force in the universe can halt gravity's inexorable pull. The core continues to shrink past the neutron star stage, past any size we can meaningfully measure, until it becomes what physicists call a singularity, a point of infinite density where the normal laws of physics break down. The formation of the event horizon happens almost simultaneously with this core collapse. As the matter falls inward past the point of no return, it creates a boundary in space-time itself, a surface beyond which nothing, not even light, can escape back to the outside universe. The black hole is born, not with a bang, but with a whisper, a cosmic sleight of hand that makes an entire stellar core simply vanish from our observable universe. This process of stellar death and black hole birth carries echoes in human cultures that go back thousands of years. The ancient Hindus spoke of Kalaratri, the night of time when the universe dissolves back into primordial darkness. In their cosmology, time itself was cyclical, with periods of creation followed by periods of dissolution, not unlike the way massive stars create heavy elements through fusion only to have them disappear forever beyond an event horizon. The story of Subrahmanyan Chandrasekhar, the Indian-American astrophysicist, who first calculated the mass limit for white dwarf stars, carries its own kind of cosmic poetry. In 1930, at the age of just 19, Chandrasekhar worked out the mathematics during a sea voyage from India to England. He discovered that stars above a certain mass, now called the Chandrasekhar limit, could never find peace as white dwarfs, but were doomed to something far more dramatic. When Chandrasekhar presented his work, He faced fierce opposition from established astronomers, particularly Arthur Eddington, who declared that there should be a law of nature to prevent a star from behaving in this absurd way. The resistance to Chandrasekhar's ideas was so intense that he was discouraged from continuing his work on stellar evolution for decades. Only much later, when observations confirmed the existence of neutron stars and black holes, did the scientific community recognize the profound importance of his calculations. He finally received the Nobel Prize in 1983, more than 50 years after his initial discovery. There's something deeply moving about this story. A young mathematician alone on a ship crossing the Indian Ocean, working out by hand the mathematics that would predict some of the most exotic objects in the universe. It reminds us that the path to understanding the cosmos is rarely straightforward, and that the universe's most profound secrets often reveal themselves first to quiet calculation rather than dramatic observation. Not all black holes are born from the deaths of individual stars. In the early universe, when matter was distributed far less evenly than it is today, gravity may have directly compressed regions of space to such extreme densities that black holes formed without any need for stellar evolution. These primordial black holes could span an enormous range of masses, from objects smaller than mountains to giants containing millions of times the mass of our Sun. The formation of supermassive black holes, the monsters that lurk at the centers of galaxies, containing millions or billions of solar masses, remains one of the great puzzles in astrophysics. These objects seem to have existed when the universe was still very young, perhaps only a few 100 million years old. There simply hasn't been enough time since the Big Bang for them to have grown from stellar mass seeds through normal accretion processes. One possibility is that the very first stars in the universe, called population 3 stars, were much more massive than any stars we see today. These primordial giants, burning in a universe that contained almost no elements heavier than hydrogen and helium, may have been hundreds of times more massive than our Sun. When they died, they could have collapsed directly into black holes massive enough to serve as seeds for the supermassive black holes we observe today. Another possibility is even more dramatic: direct collapse. Under the right conditions in the early universe, vast clouds of gas may have collapsed directly into black holes without ever forming stars at all. Computer simulations suggest this could happen when a cloud of primordial gas is heated by radiation from nearby stars, preventing it from fragmenting into smaller pieces, while still allowing it to collapse under its own gravity. There's also the fascinating possibility of intermediate mass black holes, objects too massive to form from single stellar deaths, but too small to be the supermassive monsters at galactic centers. These might form through the merger of multiple stellar mass black holes, or through the collapse of dense stellar clusters, where hundreds of stars are packed into a space smaller than our solar system. Recent gravitational wave detections have revealed black hole mergers that produce remnants in this intermediate mass range, suggesting that the universe may be full of these middle children of the black hole family. The ancient Egyptians told stories of Apep, the serpent of chaos that tried each night to devour the sun as it travelled through the underworld. In Norse mythology, the wolf Fenrir was destined to swallow the sun at Ragnarok, the end of the world. These myths speak to something deep in human psychology, the fear of light being consumed by darkness, of order giving way to chaos. But black holes, for all their fearsome reputation, are not agents of chaos. They are the universe's ultimate expression of order, regions where gravity has achieved perfect dominance over all other forces. They follow precise mathematical laws. conserving energy and angular momentum with clockwork precision. In their formation, they represent not the breakdown of natural law, but its most extreme and elegant expression. The birth of a black hole marks the end of one story, the life of a massive star, and the beginning of another. These objects will persist long after all the stars in the universe have burned out, slowly evaporating through processes so subtle they make stellar evolution look rapid by comparison. They are cosmic time capsules, preserving information about the early universe in ways we're only beginning to understand. Standing under a dark sky, looking up at the stars, you're seeing light that began its journey years, decades, or centuries ago. Somewhere among those points of light are massive stars in the final stages of their evolution, perhaps only days or hours away from the moment when their cores will collapse and disappear forever behind an event horizon. The darkness between the stars, which seems empty to our eyes, may already contain the black holes born from stars that died before life even emerged on Earth. In the darkness, invisible to our telescopes but revealed by the subtle gravitational dances of nearby objects, black holes continue their patient existence. They are the universe's way of taking matter and energy to the very edge of physics itself, then holding it there in perfect, eternal suspension. Born from the depths of the most massive stars, they represent both an ending and a beginning, the conclusion of stellar evolution and the opening of a doorway into the most extreme physics our universe has to offer. There are certain thresholds in life that, once crossed, change everything that follows. The moment when a relationship shifts from friendship to something deeper. The instant when a child takes their first independent step. The precise second when you realize you've fallen asleep and entered the realm of dreams. Event horizons are the universe's version of these irreversible boundaries, invisible lines in space that mark the point where the familiar laws of cause and effect begin to behave in ways that challenge our deepest intuitions about reality itself. The term event horizon carries a poetic weight that its discoverer, Carl Schwarzschild, might not have anticipated when he first worked out the mathematics in 1916. Schwarzschild was a German physicist and astronomer who solved Einstein's field equations just months after Einstein published his theory of general relativity. Tragically, Schwarzschild completed this work while serving on the Russian front during World War I, and he died of an autoimmune disease contracted in the trenches just days after sending his solution to Einstein. His mathematics would outlive him by more than a century, describing one of the most profound concepts in all of physics. The event horizon is fundamentally a boundary in space-time itself, not a physical surface you could touch or see, but rather a mathematical edge where the geometry of space becomes so warped that escape becomes impossible. Think of it as the cosmic equivalent of a waterfall's edge. A fish swimming upstream in a river can make progress against the current as long as it stays above the waterfall. But once it passes over that critical point, no amount of swimming can bring it back upstream. The event horizon works similarly, except instead of water flowing over rocks, it's space itself that's flowing inward toward the black hole's center. The size of this invisible boundary depends entirely on the mass of the black hole that creates it. The mathematics are surprisingly elegant. The Schwarzschild radius, as it's called, equals twice the gravitational constant times the mass, divided by the speed of light squared. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. For a black hole 1,000,000 times more massive, like those found at the centers of galaxies, the event horizon might encompass a region larger than the orbit of Mercury. But here's where our intuition begins to falter. If you were watching from a safe distance as someone fell toward a black hole, you would never actually see them cross the event horizon. As they approached that invisible boundary, time dilation would cause their image to slow down and redshift, their light stretched toward longer and longer wavelengths until they faded from view, appearing to hover forever just outside the horizon. This isn't an illusion or trick of perception. From your reference frame, they truly would take an infinite amount of time to cross that boundary. The falling person, however, would experience something completely different. From their perspective, they would pass through the event horizon in a finite amount of time, feeling nothing particularly special about the moment of crossing. The horizon isn't a wall or barrier in any physical sense. It's simply the mathematical point where the escape velocity equals the speed of light. To the falling observer, space would seem normal, and time would tick forward at its usual pace. They might not even realize they had crossed the point of no return until they tried to send a signal back to the outside universe and found that their messages could never again reach the world they had left behind. This asymmetry between different observers' experiences touches on something profound about the nature of reality itself. In our everyday world, we assume that events either happen or they don't, that there's an objective truth about whether someone has crossed a particular boundary. But near a black hole, the very concept of simultaneity breaks down. Two observers can disagree about when, or even whether, an event has occurred, and both can be correct within their own frame of reference. The mathematics that describe this strange behavior were worked out by physicists and mathematicians throughout the 20th century, each discovery adding another layer to our understanding of how extreme gravity warps the fundamental structure of space-time. The Schwarzschild solution describes the simplest case, a black hole that doesn't rotate and has no electric charge. But most real black holes rotate, some spinning so fast that they drag the very fabric of space-time around with them like honey being stirred with a spoon. These rotating black holes, described by the Kerr metric that Roy Kerr derived in 1963, create even more exotic geometries. Outside the event horizon, they generate a region called the ergosphere, where space-time itself is being dragged around so rapidly that nothing can remain stationary relative to distant observers. Within this region, you could actually extract energy from the black hole's rotation through a process Roger Penrose described in the 1970s, dropping an object into the ergosphere and having it split in such a way that one piece falls into the black hole while the other escapes with more energy than the original object possessed. The concept of an event horizon challenges not just our physics, but our philosophy. Throughout human history, cultures have recognized the importance of thresholds and boundaries. The ancient Greeks spoke of the river Styx, which separated the world of the living from the realm of the dead, a boundary that could be crossed in only one direction. Buddhist traditions describe the bardo, intermediate states between death and rebirth, where the normal rules of existence are suspended. Medieval Christian thought conceived of purgatory as a threshold realm between earthly existence and heavenly paradise. These cultural concepts all share something with the event horizon. They describe boundaries where the familiar rules no longer apply, where crossing over fundamentally changes what's possible. The event horizon is physics' version of these mythological thresholds, a place where the normal relationship between cause and effect, between sending a signal and receiving a response, is permanently severed. But the event horizon holds mysteries that go far beyond even these profound philosophical implications. In recent decades, physicists have discovered that black holes seem to encode information about everything that has ever fallen into them on their two-dimensional surfaces, like cosmic hard drives storing data in a way that seems to violate our understanding of how information should behave in three-dimensional space. This holographic principle, as it's called, suggests that all the information contained in a volume of space can be represented on the boundary of that space. For black holes, this means that every detail about every particle that has ever crossed the event horizon might be preserved in some form on the horizon itself, encoded in microscopic fluctuations of the geometry of space-time. The implications of this idea extend far beyond black holes. If the holographic principle is correct, it might mean that our own three-dimensional reality is itself a projection of information stored on some distant two-dimensional surface, that the depth and substance of our everyday experience is in some sense an illusion, a shadow cast by processes occurring on the boundary of our observable universe. Recent observations have added new wrinkles to our understanding of event horizons. The Event Horizon Telescope, a planet-spanning array of radio telescopes working together, has produced the first direct images of the event horizon of M87 star, a supermassive black hole at the center of a distant galaxy. These images show the shadow cast by the event horizon against the bright glow of superheated matter spiraling around it, the first time humans have actually seen the silhouette of space-time's ultimate boundary. The images reveal a black hole that rotates just as the mathematics predicted, with material on one side moving toward us and brightened by relativistic effects, while material on the other side moves away and appears dimmer. The event horizon appears as a dark circle, not because nothing is there, but because any light that enters that region can never escape to reach our telescopes. These observations confirm what decades of mathematical analysis had predicted, but they also raise new questions. The boundary between the bright accretion disk and the dark event horizon appears remarkably sharp, much sharper than some theoretical models had suggested. This precision hints at new physics operating at the horizon, processes we don't yet fully understand. One of the most puzzling aspects of event horizons is how they seem to reconcile quantum mechanics with general relativity in ways that still challenge our understanding. According to quantum mechanics, information cannot be destroyed. Every quantum state must evolve into some other quantum state according to precise mathematical rules. But general relativity suggests that anything falling into a black hole disappears forever behind the event horizon, taking its quantum information with it. This apparent contradiction, known as the information paradox, has spawned decades of theoretical work trying to understand how information might escape from black holes, or whether our understanding of event horizons needs to be fundamentally revised. Some physicists propose that the horizon isn't as smooth as classical general relativity suggests, but is instead a firewall where quantum effects create a barrier of high-energy radiation. Others suggest that information somehow tunnels out through quantum entanglement effects that connect the interior of the black hole to the external universe. The debate continues, touching on some of the deepest questions in physics. What is the relationship between geometry and information? How does quantum mechanics modify the predictions of general relativity in extreme environments? Are event horizons smooth surfaces or quantum firewalls? These questions don't just affect our understanding of black holes. They're central to developing a complete theory of quantum gravity that can describe the universe at its most fundamental level. The search for answers has led physicists to develop increasingly sophisticated mathematical tools and conceptual frameworks. String theory suggests that event horizons might be fuzzballs, extended objects made of tangled strings rather than smooth surfaces surrounding empty space. Loop quantum gravity proposes that space-time itself is quantized at the smallest scales, made of discrete units, that might prevent the formation of true singularities. Each approach offers different insights into how quantum mechanics and gravity might be reconciled near event horizons, but none yet provides a complete picture. The mathematics become so complex that even supercomputers struggle to follow the calculations, and the physics involved pushes beyond anything we can test experimentally. We're left to navigate these mysteries through pure thought, using mathematical elegance and theoretical consistency as our guides. Perhaps most remarkably, the study of event horizons has begun to influence fields far beyond theoretical physics. Computer scientists have found connections between black hole thermodynamics and quantum computing, suggesting that the information processing that occurs at event horizons might inspire new approaches to quantum algorithms. Philosophers grapple with what these discoveries mean for our understanding of reality, identity, and the nature of information itself. There's something almost meditative about contemplating event horizons, these invisible boundaries that exist throughout our universe, marking places where the familiar rules of space-time give way to something stranger and more subtle. They remind us that reality is far more malleable than our everyday experience suggests, that space and time themselves are dynamic entities that can be stretched, compressed, and fundamentally altered by the presence of matter and energy. Standing under a starry sky, you might wonder whether you're looking toward any of these invisible boundaries. Our own galaxy almost certainly contains millions of stellar mass black holes, the remnants of massive stars that died long before the sun was born. At the very center of the Milky Way sits Sagittarius, a star, a supermassive black hole whose event horizon spans a region about the size of Mercury's orbit. These cosmic boundaries exist in perfect silence, invisible to light, but revealed by their gravitational influence on the matter around them. They mark places where the universe has taken ordinary matter and energy and hidden them behind a mathematical veil, preserving them in a form we can describe with equations but can never directly observe. In their strange physics and philosophical implications, event horizons remind us that the universe still holds secrets at the very edge of comprehension. Boundaries where mathematics meets mystery in ways that continue to challenge and inspire our understanding of reality itself. Picture yourself standing on a beach at low tide, watching the gentle retreat of waves that just moments before lapped at your ankles. The moon, hanging pale in the afternoon sky, pulls at every drop of water with its invisible hand, lifting the vast oceans by mere inches through a force so subtle you could spend a lifetime by the shore and never feel it directly. Yet this same fundamental principle, the way gravity's strength changes with distance, becomes something far more profound and terrifying when taken to its ultimate extreme near a black hole. The difference in gravitational pull between your head and your feet as you stand on Earth is so infinitesimally small that it might as well not exist. But imagine if that difference weren't measured in billionths of a percent, but in factors of 10 or 100 or 1,000. Imagine gravity becoming so steep, so sharply focused, that the pull on your toes overwhelms the pull on your head with such intensity that your entire body begins to stretch like warm caramel left in the summer sun. This is spaghettification, and despite its whimsical name, a term that Stephen Hawking himself used, perhaps with a touch of that dry British humour that made complex physics accessible to millions, It represents one of the most elegantly brutal demonstrations of how space-time behaves when matter encounters the ultimate gravitational gradient. The name might evoke images of a cosmic pasta machine, but the reality is both more beautiful and more unsettling than any kitchen metaphor could capture. To truly understand how this stretching occurs, we need to step back and consider what gravity actually does to the fabric of reality itself. Imagine space-time as a vast, flexible sheet stretched tight across the universe. Every massive object, from the smallest grain of sand to the largest galaxy, creates a depression in this sheet, like a bowling ball placed on a trampoline. Objects moving near these depressions naturally roll toward them, following the curves that mass has carved into the geometry of space and time. Near most objects, these curves are gentle, like rolling hills in a peaceful countryside. The Earth creates a shallow, bowl-shaped depression that extends gradually outward for thousands of miles. Even our Sun, despite its immense mass, curves space-time in a way that changes smoothly and predictably as you move away from its surface. But a black hole is different. A black hole creates what mathematicians might call a cusp in space-time, a depression so sharp and deep that it resembles a funnel with sides that become steeper and steeper until they become vertical, then curve beyond vertical into realms where our normal understanding of geometry simply breaks down. As you approach this cosmic funnel, the gravitational field doesn't just become stronger, it begins to change rapidly across even small distances. This is what physicists call a gravitational gradient, and it's this gradient, not the absolute strength of gravity itself, that creates the stretching effect we call spaghettification. Your feet, being closer to the black hole than your head, experience a stronger gravitational pull. The difference might start as barely perceptible, but as you continue to fall inward, that difference grows exponentially. The mathematics that describe this process have an almost musical quality to them. The tidal force, the stretching force you experience, follows an equation where the effect is proportional to your height times the black hole's mass, divided by the cube of your distance from its center. That cubic relationship means that halving your distance increases the tidal forces eightfold. It's a crescendo that builds with mathematical precision, each moment of your fall bringing forces that grow stronger and stronger until they overwhelm every other influence in your personal universe. For a black hole with the mass of our Sun, this crescendo reaches its terrible climax long before you would reach the event horizon itself. When you are still thousands of kilometers away from that invisible boundary, the differential acceleration between your head and feet would reach about 10 times Earth's gravity. At that point, the tendons, muscles, and bones that hold your body together would begin to fail, unable to resist forces that increase relentlessly with each passing second. The experience itself would unfold with a strange, dreamlike quality. Initially, you might feel something akin to an intense stretching sensation, as if invisible hands were gently but persistently trying to pull your arms and legs in opposite directions. Your spine would be the first to respond, each vertebra beginning to separate from its neighbors as the cartilage between them stretched beyond its natural limits. You might feel a peculiar lightness in your torso, as if your chest were being drawn upward, while your hips were being pulled downward by forces too subtle to resist, yet too strong to ignore. As the stretching continued, your ribs would gradually space themselves further apart, your entire torso elongating, like a piece of warm clay being slowly pulled between gentle fingers. Your arms would extend away from your body, growing longer and thinner with each moment, while your legs stretched downward toward the black hole until you began to resemble some impossible piece of abstract sculpture, a human form reimagined by the purest mathematics of curved space-time. The transformation would be both gradual and inexorable. You might watch your own hands as they move further and further from your eyes, your arms extending like rubber bands until your fingertips seem to belong to someone else entirely. Your reflection, could you somehow see it, would show a being stretched across meters, then tens of meters, then hundreds. Your consciousness, somehow still intact, within this elongated geometry of flesh and bone that followed the invisible contours of space-time itself. But the process wouldn't stop with the gross anatomy of bones and muscles. As the tidal forces continued to strengthen, they would begin to affect smaller and smaller structures within your body. The cells themselves would start to stretch, their membranes distorting as the very molecules that give them structure were pulled in different directions by the differential gravity. The proteins that maintain cellular integrity would begin to unfold, their carefully evolved shapes, maintained across billions of years of evolution, succumbing to forces that biology had never encountered and could never have prepared for. Eventually, even the atomic bonds that hold matter together would surrender to the relentless tidal gradient. Individual atoms would be torn apart, their electrons separated from their nuclei by forces stronger than the electromagnetic attraction that normally binds them together. You would become not just a stretched version of yourself, but a stream of subatomic particles, each one following its own independent trajectory through the curved space-time around the black hole, all of them dancing to the same gravitational music, but each hearing a slightly different rhythm. This might sound like the stuff of science fiction horror, but the universe presents us with a remarkable plot twist. The strength of spaghettification depends not just on the mass of the black hole, but on the relationship between that mass and the size of the event horizon. More massive black holes, counterintuitively, create gentler tidal forces at their event horizons. This happens because larger black holes have event horizons that are proportionally farther from their central singularities, and since tidal forces depend on how rapidly gravity changes with distance, a more massive black hole creates a more gradual gravitational gradient at its boundary. The supermassive black hole at the center of our own galaxy, Sagittarius A star, contains roughly 4 million times the mass of our Sun. Its event horizon spans a region larger than the orbit of Mercury. If you were falling toward this cosmic giant, you could actually cross the event horizon and survive the experience, at least initially. The tidal forces at the boundary would be no stronger than the differential gravity you experience between your head and feet while standing on Earth. You would enter the ultimate point of no return feeling, perfectly normal, perfectly intact, blissfully unaware that you had just crossed a threshold beyond which the rest of the universe could never again receive any signal from you. The cultural resonance of stretching and transformation runs like a hidden river through human mythology and spiritual practice. Ancient stories speak of shamanic journeys, where the spirit body extends across vast distances, experiencing unity with cosmic forces that transcend ordinary physical limitations. In many traditions, the ability to stretch or elongate the body represents a kind of spiritual accomplishment, a way of transcending the normal boundaries of physical existence. Medieval alchemists spoke of the process of solve et coagula, dissolve and coagulate, the idea that transformation requires first breaking down existing structures before rebuilding them in new forms. The spaghettification process embodies this principle taken to its absolute extreme, where the dissolution is so complete that the very atoms of matter are separated and reorganized according to the fundamental geometry of space-time itself. In Hindu and Buddhist cosmology, the concept of dissolution plays a central role in understanding the cyclical nature of existence. During the cosmic dissolution known as pralaya, all forms return to their primordial state, individual structures dissolving back into the undifferentiated matrix from which they emerged. Spaghettification represents a kind of localized pralaya, where matter encounters forces so extreme that it returns to its most basic components, individual particles following the most fundamental laws of physics as they spiral inward toward a mathematical point. The process affects not only living beings, but any object that ventures too close to a black hole's gravitational embrace. Imagine a spacecraft, its metal hull gleaming in the pale light, reflected from the accretion disk, as it approaches within the tidal radius of a stellar mass black hole. The first signs of distress would be subtle, rivets beginning to strain as the ship's structure experiences forces it was never designed to withstand. The bow of the craft, pointing toward the black hole, would feel a stronger pull than the stern, creating stresses that would gradually overcome the electromagnetic forces holding the atomic lattice of the hull together. As the stretching progressed, the spacecraft would begin to deform, its sleek engineering compromised by the inexorable mathematics of curved spacetime. Bulkheads would buckle, cables would snap, and eventually the entire vessel would transform into a stream of metallic debris, each piece following its own trajectory through the gravitational funnel created by the black hole. Even the information stored in the ship's computers would be dispersed, the delicate magnetic patterns that encoded data scattered as the storage devices themselves were torn apart at the molecular level. When stars encounter the tidal forces around supermassive black holes, the results are some of the most spectacular displays of light and energy in the observable universe. Picture a star, perhaps similar to our own Sun, that has spent billions of years maintaining its perfect spherical shape through the delicate balance between gravitational collapse and the outward pressure of nuclear fusion. As it approaches within a few million kilometers of a supermassive black hole, this ancient equilibrium is suddenly and catastrophically disrupted. The side of the star facing the black hole begins to feel a gravitational pull, thousands of times stronger than the pull on the star's opposite hemisphere. The star, which has maintained its integrity for eons, suddenly finds its outer layers streaming away in brilliant ribbons of plasma. Each tendril of stellar material follows its own graceful arc through space, the superheated gas glowing with temperatures of millions of degrees as it spirals inward toward the event horizon. From a great distance, such a tidal disruption event might resemble a cosmic flower blooming in reverse, its petals of incandescent gas unfolding across millions of kilometers as they trace the invisible geometry of curved space-time. The light from these events can briefly outshine entire galaxies, visible to our telescopes across billions of light years as sudden brightenings that persist for months or years as the stellar debris continues its final journey inward. These cosmic lighthouses serve as beacons that reveal the presence of otherwise invisible supermassive black holes lurking at the centers of distant galaxies. Each tidal disruption event is like a signal fire lit in the darkness of intergalactic space, announcing that somewhere in that distant realm, matter has encountered the ultimate expression of gravitational force and been transformed according to the most fundamental laws of physics. Modern computer simulations have allowed scientists to model the spaghettification process with exquisite detail, following millions of individual particles as they experience the increasingly intense tidal forces near black holes. These calculations reveal patterns of almost mathematical beauty, swirling vortices of matter that persist for fractions of a second before being torn apart, shock waves that propagate through the falling debris, and magnetic fields that become twisted into elaborate geometries as they're dragged along with the infalling material. The most sophisticated simulations now include quantum mechanical effects, showing how the fundamental uncertainty principle begins to influence the behavior of matter as it's compressed and stretched by extreme tidal forces. At the smallest scales, the smooth, classical picture of spaghettification gives way to something more subtle and strange, where the very concept of a particle's position becomes fuzzy, and the distinction between matter and energy begins to blur. These theoretical investigations are pushing the boundaries of our understanding, revealing connections between gravity, quantum mechanics, and information theory that may ultimately lead to a complete description of how space, time, and matter behave under the most extreme conditions imaginable. Each new calculation adds another piece to a puzzle that spans from the largest structures in the universe to the smallest possible scales of physical reality. There's something almost meditative about contemplating the gradual, patient nature of spaghettification. Unlike explosive or sudden forms of destruction, tidal stretching unfolds with a kind of cosmic inevitability that mirrors the deeper rhythms of the universe itself. It's a process that reveals the hidden architecture of space-time, making visible through its effects the invisible curvature that surrounds every massive object. As we continue our gentle journey into the heart of black hole physics, spaghettification serves as a bridge between the familiar world of gravity, as we experience it on Earth, and the exotic realm where space and time themselves become malleable. In our next exploration, we'll discover that black holes don't just stretch matter across space. They stretch time itself, creating regions where minutes can become hours, where the familiar tick of cosmic clocks slows to a rhythm that exists nowhere else in the universe, where the very flow of causality bends to accommodate the supreme authority of curved space-time. Imagine two clocks, identical in every detail, their mechanisms crafted with the precision that only centuries of human ingenuity could achieve. One sits quietly on your desk, marking the familiar rhythm of seconds that has governed human life since we first learned to divide daylight into measurable portions. The other begins a journey downward through increasingly curved space-time, approaching the event horizon of a black hole. As you watch from your safe distance, something extraordinary happens. The travelling clock begins to slow down, its hands moving more and more sluggishly until they seem to freeze entirely at the moment it crosses that invisible boundary where space and time themselves surrender to gravity's ultimate authority. This is gravitational time dilation, and it represents perhaps the most profound challenge to our intuitive understanding of time itself. We experience time as universal, as absolute, the same for everyone, everywhere, flowing forward at a steady, unchanging pace, like a cosmic metronome that keeps the entire universe in sync. But Einstein's general relativity reveals something far more subtle and strange. Time is not a fixed backdrop against which events unfold, but rather a flexible dimension of reality itself. Something that can be stretched, compressed, and warped by the presence of matter and energy. The mathematics that describe this warping are deceptively simple, yet they lead to consequences that challenge every assumption we might have about the nature of existence itself. Near a massive object, time literally runs slower than it does in regions of weaker gravity. The effect is described by an equation that relates the flow of time to the strength of the gravitational field. The stronger the gravity, the more dramatically time dilates, stretching moments into longer and longer intervals until, at the event horizon of a black hole, time appears to stop entirely. This isn't merely a theoretical curiosity or mathematical abstraction. Every day, the global positioning system satellites that help us navigate from place to place must account for the fact that time runs slightly faster in their orbits than it does on Earth's surface. The difference is tiny, about 38 microseconds per day, but it's real and measurable. Without correcting for this relativistic effect, GPS would accumulate errors of several kilometers within just a few hours, making the system useless for navigation. Near a black hole, these time dilation effects become so extreme that they transform the very meaning of temporal experience. If you were falling toward a black hole while your friend watched from a safe distance, the two of you would experience time in fundamentally different ways. From your perspective, falling freely through the curved space-time, your watch would continue to tick at its normal rate. Minutes would feel like minutes, hours like hours. You would cross the event horizon in what seemed like a reasonable amount of time, perhaps a few minutes or hours depending on the mass of the black hole. But your friend, watching from afar, would see something completely different. As you approach the event horizon, they would observe your clock running slower and slower. Your movements would appear to become sluggish, as if you were swimming through increasingly thick honey. The light from your spacecraft would shift toward longer wavelength, becoming redder and dimmer as gravity stretched each photon during its climb out of the deepening gravitational well. From your friend's perspective, you would never quite reach the event horizon. Instead, you would appear to slow down asymptotically, your image growing fainter and redder until it faded beyond detection, but never actually crossing that final boundary. In their reference frame, it would take literally forever for you to complete that final journey. An infinite amount of time stretched across the approach to the horizon, each second of your experience corresponding to longer and longer periods in the outside universe. This asymmetry reveals something profound about the nature of space-time itself. There's no universal now, no cosmic clock that ticks the same for all observers. Instead, the flow of time is intimately connected to the curvature of space, and different observers moving through different gravitational fields will experience different rates of temporal passage. What seems like a brief journey to you becomes an eternal vigil to your distant friend. The roots of this understanding stretch back to Einstein's early insights about the relationship between gravity and acceleration. In 1907, he realized that someone in a windowless elevator couldn't tell the difference between being pulled downward by gravity and being accelerated upward in empty space. This equivalence principle became the foundation for general relativity, leading to the recognition that gravity isn't really a force at all, but rather the curvature of space-time itself. This curvature affects not just the motion of objects, but the very flow of time. Einstein imagined standing in a gravitational field and shining a light towards someone higher up, where gravity is slightly weaker. As the light climbs against gravity, it loses energy. And since energy and frequency are related by Planck's constant, the light becomes redshifted, its wavelength stretched toward the red end of the spectrum. This gravitational redshift is intimately connected to time dilation, both arising from the same underlying geometry of curved space-time. The effect becomes more dramatic as gravitational fields become stronger. Around a neutron star where gravity is so intense that matter is compressed to nuclear densities, time dilation becomes noticeable even over the span of a human lifetime. If you could somehow survive on the surface of such an object for what felt like a year, people watching from Earth would see you experiencing that year over the course of several months or even weeks, depending on the star's exact mass and density. But around black holes, time dilation reaches truly extraordinary extremes. The mathematical description involves what physicists call the Schwarzschild metric, a solution to Einstein's field equations that describes the geometry of space-time around a spherically symmetric mass. As you approach the Schwarzschild radius, the location of the event horizon, the time dilation factor approaches infinity. What this means is that any finite amount of proper time experienced by someone falling into the black hole corresponds to an infinite amount of coordinate time as measured by distant observers. This creates what might seem like a paradox. If it takes forever for anything to actually cross the event horizon as seen from the outside, how can black holes ever form in the first place? How can they grow by accreting matter if that matter never quite reaches the horizon? The resolution lies in understanding that there are different ways to describe the same physical reality, different coordinate systems that can be used to map the geometry of space-time around black holes. From the perspective of the infalling matter, the crossing happens in finite time and feels perfectly normal. The event horizon isn't a physical barrier or wall, it's simply a coordinate surface, a mathematical boundary in space-time. The matter crosses this boundary and continues falling toward the central singularity, where the curvature of space-time becomes infinite and our current understanding of physics breaks down. The apparent contradiction between these different perspectives has deep implications for our understanding of information and entropy in the universe. If matter takes forever to cross the event horizon as seen from outside, then in some sense the information it carries never actually disappears from the observable universe. This insight has led to the development of black hole complementarity, a principle suggesting that the same physical process can be described in two apparently contradictory but equally valid ways, depending on the observer's perspective. Cultural traditions throughout history have grappled with concepts that parallel these insights about the relative nature of time. Ancient Hindu and Buddhist cosmologies speak of different realms where time flows at different rates, heavenly realms where a single day corresponds to years of earthly time, or underworld regions where eons pass in what seems like moments. These mythological frameworks developed thousands of years before Einstein, capture something essential about the possibility that time itself might not be universal or absolute. The Greek concept of kairos, qualitative time that depends on meaning and significance, stands in contrast to chronos, the quantitative time measured by clocks and calendars. Black holes seem to exist at the boundary between these two concepts, where the objective passage of chronos becomes so distorted that it transforms into something more like kairos, where moments can stretch toward infinity and the normal relationship between cause and effect begins to break down. Einstein himself initially resisted some of the more extreme implications of his own theory. When presented with solutions to his field equations that described what we now call black holes, he expressed doubt that such objects could actually exist in nature. The mathematics seemed too strange, the physical implications too radical. He couldn't quite accept that the universe would allow matter to collapse so completely that it would disappear from observable reality, taking with it any possibility of communication or causal influence on the outside world. The observational confirmation of time dilation effects near massive objects has provided some of the strongest evidence for general relativity. The Hafele-Keating experiment of 1971 used atomic clocks flown on commercial airliners to directly measure the tiny time dilation effects predicted by relativity theory. Atomic clocks are so precise that they can detect time differences of less than a nanosecond, and the results matched Einstein's predictions with remarkable accuracy. More dramatic confirmations have come from observations of the binary pulsar system, PSRB 1913 plus 16, discovered by Russell Hulse and Joseph Taylor in 1974. This system consists of two neutron stars orbiting each other with orbital periods of just a few hours. As they spiral inward due to energy loss from gravitational wave radiation, their orbital motion becomes increasingly relativistic, and the time dilation effects become measurable through precise timing of the pulsar's radio emissions. The data from this system provided the first indirect evidence for gravitational waves, decades before the LIGO detectors achieved direct detection. But perhaps more importantly for our current discussion, they demonstrated that time dilation effects predicted by general relativity occur exactly as the theory predicts, even in the extreme gravitational environments around neutron stars. Recent observations of stars orbiting the supermassive black hole at the center of our galaxy have provided even more dramatic demonstrations of relativistic effects. The star S2, which follows a highly elliptical orbit that brings it within about 100 astronomical units of Sagittarius A star, experiences significant time dilation and gravitational redshift at closest approach. When S2 reached periapsis in 2018, its light showed exactly the redshift and time dilation effects predicted by general relativity. These observations represent a remarkable triumph of theoretical physics. The same equations that Einstein wrote down over a century ago, based on abstract principles about the geometry of spacetime, accurately predict the behavior of matter and light in some of the most extreme gravitational environments in the universe. The mathematics developed to describe imaginary thought experiments involving elevators and train stations turn out to govern the motion of real stars around real black holes. The phenomenon of frame dragging adds another layer of complexity to time dilation effects around rotating black holes. When a massive object spins, it literally drags space-time along with it, creating a region called the ergosphere, where the normal relationship between space and time becomes even more distorted. Within the ergosphere, it becomes impossible to remain stationary relative to distant observers. The rotation of space-time itself carries everything along with it. This frame-dragging effect was first described mathematically by the Austrian physicist Roy Kerr in 1963 in what's now called the Kerr metric. Most real black holes are thought to rotate, some at significant fractions of the maximum possible rate. So understanding these effects is crucial for describing the actual geometry of spacetime around these objects. The time dilation experienced by matter in the ergosphere is different from that around a non-rotating black hole, modified by the complex interplay between gravitational redshift and the rotation of space-time itself. Imagine standing at the edge of a cosmic whirlpool, watching space-time itself swirl around a spinning black hole like water circling a drain. Time doesn't just slow down, it begins to twist, following helical paths through four-dimensional space-time as the rotation couples temporal and spatial coordinates in ways that have no analogue in our everyday experience. The very concept of simultaneity becomes ambiguous, with events that appear to happen at the same time, from one perspective occurring in different temporal orders when viewed from another reference frame. These effects have practical implications for any future exploration of black holes. A spacecraft approaching a rotating black hole would experience time dilation that depends not just on its distance from the event horizon, but also on its direction of motion relative to the black hole's spin. Moving in the same direction as the rotation would reduce the effective gravitational field experienced by the spacecraft, while moving against the rotation would enhance it. The Penrose process, proposed by Roger Penrose in 1969, suggests that it might even be possible to extract energy from a rotating black hole by dropping matter into the ergosphere in just the right way. If an object entering the ergosphere splits into two pieces, with one piece falling into the black hole while the other escapes, the escaping piece can carry away more energy than the original object possessed. This process would gradually slow down the black hole's rotation, converting its rotational energy into kinetic energy of the escaping matter. Such possibilities hint at advanced civilizations that might use black holes as cosmic power sources, tapping the enormous energies stored in their rotation through carefully orchestrated interactions with the ergosphere. The time dilation effects around such engineering projects would create temporal landscapes, unlike anything in our current experience, with different regions of space experiencing vastly different rates of time passage. The philosophical implications of gravitational time dilation extend far beyond physics into questions about the nature of existence, identity, and consciousness itself. If your subjective experience of time can differ so dramatically from that of other observers, what does it mean to say that events happen at the same time? How do we maintain coherent concept of causality when the temporal order of events depends on the observer's gravitational environment? Some philosophers have suggested that gravitational time dilation challenges our deepest assumptions about personal identity over time. If you were to fall into a black hole while your twin remained safely outside, the two of you would gradually drift apart, not just in space, but in time itself. From your twin's perspective, you would effectively become frozen at the moment of crossing the event horizon, your image fading but never quite disappearing. From your perspective, you would continue to exist and experience the passage of time normally, but you would be causally disconnected from the outside universe forever. These thought experiments push at the boundaries of what it means to exist in time, suggesting that temporal experience is far more subjective and observer-dependent than our everyday intuitions would suggest. The universe revealed by general relativity is one where time itself becomes malleable, where the cosmic clockwork that seems so fundamental to our experience of reality turns out to be relative, contextual, and ultimately mysterious. As we continue our journey deeper into the heart of black hole physics, time dilation serves as a bridge between the familiar world of Newtonian mechanics and the strange realm where space and time become unified into a single dynamic entity. In our next exploration, we'll venture to the very center of this cosmic mystery, where the curvature of space-time becomes so extreme that our current understanding of physics itself begins to break down, leading us into regions where infinity awaits not as a mathematical abstraction, but as a physical reality that challenges the very foundations of what we think we know about the universe. Picture a map of the world that becomes increasingly detailed as you approach a particular city, showing first countries, then states, then individual streets and buildings with ever greater precision. Now imagine that, as you continue to zoom in, the level of detail doesn't just increase, it becomes infinite. Every point on the map opens up into new layers of complexity, each one containing more information than the layer before, until you're looking at something that defies the very concept of finite description. This is what mathematicians call a singularity, and at the heart of every black hole, hidden behind the veil of the event horizon, lies what may be the most profound example of this concept that physics has yet encountered. The word singularity carries an almost mystical weight in the vocabulary of physics, suggesting something that stands apart from the ordinary rules that govern the rest of reality. In mathematical terms, a singularity is simply a point where a function becomes undefined, where the normal equations break down and give impossible answers like division by zero or infinity. But when Einstein's equations of general relativity predict a singularity at the center of a black hole, they're not just describing a mathematical curiosity, They're pointing toward a region of space-time where the very concepts of space, time, and matter as we understand them may cease to have meaning. According to our best current theories, at the center of every black hole lies a point of infinite density and zero volume, a place where all the matter that has ever fallen past the event horizon is compressed into a space so small it makes the nucleus of an atom seem vast by comparison. The curvature of space-time at this point becomes infinite, creating what physicists call a curvature singularity. It's a place where the smooth geometry that Einstein used to describe gravity breaks down completely, leaving us with mathematical expressions that simply say infinity, where they should give us meaningful physical quantities. But this description, dramatic as it sounds, is almost certainly incomplete. The appearance of infinities in a physical theory is usually a sign that the theory has reached the limits of its applicability, like trying to use the rules of chess to describe the behavior of water, or applying the equations of fluid dynamics to understand the motion of individual atoms. When general relativity predicts infinite density and curvature, it's probably telling us that we need new physics, a deeper theory that can describe what really happens when matter is compressed beyond the point where our current understanding applies. The journey toward understanding singularities began in the early decades of the 20th century as mathematicians and physicists explored the implications of Einstein's field equations. In 1916, just months after Einstein published his theory of general relativity, Carl Schwarzschild found an exact solution that described the space-time geometry around a spherically symmetric mass. Schwarzschild derived this solution while serving on the Russian front during World War I, completing the work just days before his death from an autoimmune disease contracted in the trenches. The Schwarzschild solution revealed two troubling features: places where the mathematical expressions seem to blow up and become infinite. One of these occurred at what we now call the event horizon, but further analysis showed that this infinity was merely an artifact of the coordinate system Schwarzschild had chosen, like the apparent singularity at the North Pole on a standard map of the Earth, which disappears when you use different coordinates, but the other infinity, at the very center of the solution, proved to be something deeper and more fundamental. For decades, physicists hoped that these central singularities might be avoided through some mechanism that wasn't yet understood. Perhaps matter couldn't actually be compressed to infinite density. Perhaps some new force or quantum effect would intervene before the collapse became truly extreme. Perhaps the formation of singularities was prevented by some cosmic censorship principle that protected the universe from the mathematical violence that seemed to lurk at the hearts of black holes. These hopes were gradually eroded by a series of mathematical theorems developed throughout the mid-20th century. In the 1960s, Roger Penrose proved that once an event horizon forms around a collapsing mass, the formation of a singularity inside that horizon becomes inevitable. The matter cannot halt its collapse, cannot find equilibrium, cannot escape its fate. It must continue falling inward until it reaches a state of infinite density and zero volume, regardless of pressure forces, rotation, or any other physical effects that might try to stop the process. Penrose's singularity theorems, for which he was awarded the Nobel Prize in Physics in 2020, represent one of the most profound results in theoretical physics. They demonstrate that singularities are not exotic curiosities that might occur under special circumstances, but rather generic features of Einstein's theory, inevitable consequences of gravitational collapse that occurs whenever matter becomes sufficiently concentrated. The theorems are purely mathematical, making no assumptions about the specific physics of matter under extreme conditions. Yet they prove with logical certainty that certain types of space-time geometry must contain regions where curvature becomes infinite. Stephen Hawking extended Penrose's work to show that the entire universe, when traced backward in time, must have emerged from a cosmological singularity, the Big Bang itself. If general relativity is correct, then our entire cosmos began in a state of infinite density and temperature, a moment when the normal laws of physics simply didn't apply. The same mathematical inevitability that governs the formation of black hole singularities also governs the origin of everything we can observe. But what does it actually mean for density to become infinite? Our everyday experience of matter involves atoms separated by relatively vast distances, with most of the volume of ordinary objects consisting of empty space between atomic nuclei and electrons. Even in the densest forms of matter we encounter, the cores of neutron stars, where atomic nuclei are crushed together until they touch, there's still structure, still organization, still meaningful concepts of distance and volume. As matter falls toward a black hole singularity, this organization gradually breaks down. First, the atoms themselves are torn apart by tidal forces, their electrons stripped away to leave bare nuclei. Then the nuclei themselves begin to merge and compress, forming exotic forms of matter that exist nowhere else in the universe. The familiar particles that make up ordinary matter, protons, neutrons, electrons, may cease to exist as distinct entities, transformed into more fundamental constituents, or entirely new forms of organization that we can barely imagine. At some point in this process, quantum mechanical effects must become important. The Heisenberg uncertainty principle tells us that as particles are compressed into smaller and smaller volumes, their momenta become increasingly uncertain, creating quantum fluctuations that grow stronger as the compression continues. These fluctuations should eventually become so large that they overwhelm the classical gravitational forces driving the collapse. But exactly how this happens remains one of the great unsolved problems in physics. Different approaches to quantum gravity suggest different pictures of what might replace the classical singularity. In string theory, the fundamental constituents of matter are not point particles, but tiny vibrating strings or membranes. As matter approaches what would classically be a singularity, these extended objects might become stretched and tangled in ways that prevent the formation of true infinite density. The result could be a fuzzball, a region of highly excited strings that mimics a black hole from the outside, but contains no actual singularity at its center. Loop quantum gravity, another approach to unifying quantum mechanics with general relativity, suggests that space-time itself might be discrete rather than continuous at the smallest scales. In this picture, matter approaching a singularity would encounter a kind of quantum bounce, where the collapse halts and reverses when the density reaches some maximum value, determined by the fundamental granularity of space and time. The classical singularity would be replaced by a quantum bridge connecting the black hole to some other region of space-time, possibly another universe entirely. These speculative ideas push far beyond what can currently be tested experimentally, but they hint at the possibility that the terrifying infinities predicted by classical general relativity might be tamed by a deeper understanding of quantum mechanics and space-time geometry. The singularities that appear so inevitable in Einstein's theory might turn out to be artifacts of our incomplete understanding, mathematical mirages that dissolve when we develop the proper theoretical tools to see beyond them. Yet even if quantum effects prevent the formation of true singularities, they would do so only at scales so small and densities so extreme that the differences might be academic for practical purposes. Whatever quantum replacement exists for the classical singularity would still represent a region where matter has been compressed far beyond anything in our normal experience, where the familiar properties of space and time have been transformed into something alien and incomprehensible. The different types of singularities predicted by general relativity each tell their own story about the relationship between matter, energy, and space-time geometry. A Schwarzschild black hole, formed from a perfectly spherical collapse, contains what's called a space-like singularity, a moment in time rather than a place in space, representing the final endpoint of the collapsing matter's world line through space-time. This singularity exists in the future of anyone who crosses the event horizon, an inevitable destination that can be postponed but never avoided. Rotating black holes, described by the Kerr solution that Roy Kerr discovered in 1963, contain a different kind of singularity, a ring rather than a point, with properties that seem even stranger than their non-rotating cousins. The mathematics suggests that this ring singularity might be time-like rather than space-like, existing as a place rather than a moment, and possibly even allowing for the bizarre possibility of closed time-like curves, paths through space-time that loop back on themselves, potentially permitting forms of time travel that violate our normal understanding of causality. These mathematical possibilities highlight how far the predictions of general relativity diverge from our everyday intuitions about the nature of reality. The theory that so successfully describes the gentle bending of starlight around the sun and the precise orbits of planets also predicts regions where time becomes space, where cause and effect break down, and where the very concepts we use to describe physical reality lose their meaning. Ancient philosophical traditions have long grappled with concepts that parallel these modern insights about the limits of physical description. The Hindu concept of Bindu represents the point source of creation, the dimensionless seed from which all of existence unfolds. In this cosmological framework, the universe emerges from a state that transcends ordinary concepts of space, time, and causality, not unlike the way modern cosmology traces the Big Bang back to an initial singularity that existed before the formation of space and time as we know them. Medieval Christian mysticism spoke of the coincidentia, oppositorum, the unity of opposites, describing mystical experiences where contradictory concepts somehow become reconciled in a higher understanding that transcends rational thought. The mathematical singularities at the hearts of black holes seem to embody this principle taken to its logical extreme. Places where the finite and infinite, the spatial and temporal, the physical and metaphysical somehow merge into something that our current conceptual frameworks cannot adequately describe. Zen Buddhist philosophy employs the concept of shunyata, often translated as emptiness or void, to describe a state that contains all potential while manifesting none of the particular characteristics we normally use to distinguish one thing from another. The mathematical singularity, with its infinite density and zero volume, its complete absence of spatial extension, coupled with the presence of all the mass energy that has fallen into the black hole, seems to embody a physics version of this paradoxical emptiness that somehow contains everything. These parallels don't prove that ancient mystics somehow anticipated modern physics, but they do suggest that human beings have long intuited the possibility of states of existence that transcend our ordinary categories of thought. The mathematical singularities predicted by general relativity push us towards similar transcendence, forcing us to confront the limits of physical description and to acknowledge that reality might contain aspects that lie forever beyond the reach of scientific understanding. The cosmic censorship conjecture, proposed by Roger Penrose in 1969, suggests that nature has a built-in mechanism for protecting the rest of the universe from the mathematical violence of naked singularities. According to this hypothesis, whenever matter collapses to form a singularity, that singularity is always hidden behind an event horizon, safely sealed away from the outside world, where it cannot influence the behavior of matter and energy in the broader universe. If cosmic censorship holds true, then singularities would be like cosmic secrets, profound mysteries that exist but can never be directly observed or investigated. We could infer their presence from the behavior of event horizons and the gravitational effects of black holes, but we could never directly probe their properties or test our theories about what really happens when matter is compressed beyond the classical breaking point of space-time geometry. Recent research has revealed possible exceptions to cosmic censorship, mathematical solutions to Einstein's equations that describe naked singularities, regions of infinite curvature that are not hidden behind event horizons. These solutions typically require very special initial conditions or exotic forms of matter, leading most physicists to believe that they probably don't occur in the real universe, but their mere mathematical possibility highlights how much we still don't understand about the relationship between singularities, event horizons, and the fundamental structure of space-time. The study of singularities has also revealed deep connections between gravity, thermodynamics, and information theory that continue to reshape our understanding of physical reality. Black holes seem to have temperatures and entropies, suggesting that they are thermodynamic objects with internal structure, despite appearing completely featureless from the outside. The entropy of a black hole is proportional to the area of its event horizon rather than its volume, hinting at a holographic principle where three-dimensional physics might be encoded on two-dimensional surfaces. These insights have led to the development of the gauge-gravity correspondence, a mathematical duality that relates certain theories of quantum gravity to quantum field theories living on the boundary of spacetime. In this framework, the physics of black hole singularities might be describable in terms of more conventional quantum mechanical systems, opening up new avenues for understanding what happens when matter is compressed beyond the reach of classical description. Modern computational techniques have allowed physicists to simulate the formation and evolution of black holes with unprecedented detail, following matter as it falls through the event horizon and approaches the central singularity. These simulations reveal complex dynamics involving plasma physics, magnetic fields, and relativistic fluid flows, but they inevitably break down as the matter approaches the region where classical physics predicts infinite density. The computers simply cannot follow the evolution beyond the point where the mathematical expressions become undefined. Future developments in theoretical physics may eventually resolve the mystery of what lies at the heart of black holes, but for now the singularity remains one of nature's most profound puzzles. It represents a boundary of human knowledge, a place where our most successful theories of space, time, and matter acknowledge their own limitations and point toward the need for deeper understanding. As we continue our exploration of black hole physics, the concept of the singularity serves as a reminder that the universe still holds secrets that challenge the very foundations of scientific description. These mathematical points of infinite density may be artifacts of incomplete theories, or they may represent genuine features of reality that transcend our current capacity for understanding. Either way, they mark the boundary between the known and unknown, between the describable and mysterious, pointing us toward realms where the familiar concepts of physics give way to something far stranger and more wonderful than our everyday experience could prepare us to imagine. In our next journey, we'll step back from these mathematical abstractions to explore how black holes reveal themselves to our telescopes and instruments, emerging from theoretical possibility into observed reality through some of the most ingenious detective work in the history of science. Imagine trying to map the locations of every invisible person in a crowded room using only the sounds of their footsteps, the movement of objects they touch, and the shadows they cast when they pass in front of bright lights. This is essentially the challenge astronomers faced when they first began searching for black holes, objects so fundamentally dark that they absorb every photon that ventures too close, revealing their presence only through the subtle gravitational choreography they impose on everything around them. The quest to find these cosmic phantoms began not with grand space telescopes or sophisticated instruments, but with patient observations of ordinary stars that seemed to be dancing with invisible partners. In the early 1970s, astronomers noticed something peculiar about a star in the constellation Cygnus. This star, designated HDE 226868, appeared to be orbiting around an unseen companion every 5.6 days, its motion revealing the presence of something massive yet completely dark. Something that pulled on the star with enough gravitational force to make it wobble back and forth across the sky in a cosmic waltz with an invisible partner. The story of Cygnus X1, as this system came to be known, reads like a detective novel written in the language of physics. The visible star, a blue supergiant about 20 times more massive than our Sun, betrayed the presence of its hidden companion through the subtle Doppler shifting of its light. As the star moved toward us in its orbit, its light became slightly bluer. As it moved away, it became slightly redder. These shifts were tiny, changes in wavelength measured in fractions of a nanometer, but they were regular, predictable, and told a story of two massive objects locked in gravitational embrace. But the real breakthrough came when astronomers turned X-ray telescopes toward the system. They found that Cygnus X1 was one of the brightest X-ray sources in the sky, pouring out high-energy radiation with an intensity that seemed to defy explanation. The X-rays weren't coming from the visible star itself, which was far too cool to produce such energetic photons. Instead, they appeared to be generated by something happening in the space between the two objects, matter being heated to temperature of millions of degrees Celsius as it spiraled inward toward the invisible companion. Picture the scene. Material from the blue supergiant, loosely bound by the star's gravity, begins to drift toward its unseen partner. As this gas falls deeper into the companion's gravitational well, it speeds up, following increasingly tight spiral paths that compress and heat the material until it glows with the fierce radiance of temperatures found nowhere else in nature except in the cores of stars. The matter doesn't fall directly inward, but instead forms what astronomers call an accretion disk, a swirling pancake of superheated plasma that slowly feeds its way toward the central object. The physics of these accretion disks is both beautiful and violent. Friction between different layers of the spiraling gas converts orbital energy into heat, gradually causing the material to lose angular momentum and drift inward. The inner regions of the disk, where matter moves at significant fractions of the speed of light, become so hot that they emit X-rays, electromagnetic radiation, energetic enough to penetrate through much of the matter that would absorb visible light. These X-rays serve as the calling card of black holes, allowing us to detect objects that would otherwise remain completely invisible. The mass of the invisible object in Cygnus X1 clinched the case for astronomers. By carefully measuring the orbital motion of the visible star, they could calculate the mass of its unseen companion using the same Newtonian mechanics that Johannes Kepler had used to understand planetary motion 4 centuries earlier. The result was shocking. The invisible object contained at least 10 times the mass of our Sun, far exceeding the theoretical maximum mass that any neutron star could support. This was the smoking gun that convinced most astronomers that black holes weren't just mathematical curiosities, but real objects existing in our galaxy. The Tolman-Oppenheimer-Volkoff limit had established that neutron stars could contain no more than about 3 solar masses before collapsing further. An invisible 10 solar mass object that was actively accreting matter and emitting X-rays could only be one thing: a region of space-time so curved that not even light could escape. The discovery of Cygnus X1 opened the floodgates for black hole astronomy. Over the following decades, astronomers identified dozens of similar systems throughout our galaxy. Binary star systems where one member had evolved beyond the neutron star stage into something even more compact and exotic. Each discovery added another piece to the puzzle, revealing a population of stellar mass black holes scattered throughout the Milky Way like dark seeds left behind by the deaths of the most massive stars. But perhaps even more remarkable was the growing evidence for supermassive black holes lurking at the centers of galaxies. The first hints came from observations of quasars, quasi-stellar objects that appeared as single points of light in optical telescopes, but blazed with the luminosity of 1,000 galaxies. These distant beacons, visible across billions of light-years, seem to require energy sources far more compact and efficient than any collection of ordinary stars could provide. The only known mechanism capable of producing such enormous amounts of energy from such a small volume was the accretion of matter onto supermassive black holes. When material falls into the gravitational well of a black hole containing millions or billions of solar masses, it can convert up to about 10% of its rest mass into radiant energy, an efficiency that makes nuclear fusion look almost wasteful by comparison. The quasars, astronomers realized, were essentially cosmic lighthouses powered by matter falling into supermassive black holes in the early universe. The confirmation that our own galaxy harbors such a monster came through decades of patient observation of stars orbiting the galactic center. Using increasingly sophisticated telescopes, astronomers tracked individual stars as they followed elliptical paths around an invisible gravitational center in the constellation Sagittarius. One star, designated S2, provided particularly compelling evidence as it completed a highly elongated orbit that brought it within just a few hundred astronomical units of the central object every 16 years. When S2 reached its closest approach in 2018, it was moving at more than 7,000 kilometers per second, about 2% of the speed of light. At these velocities, the effects of Einstein's relativity become clearly measurable. The star's light showed exactly the gravitational redshift and time dilation effects predicted by general relativity, providing not just evidence for the existence of a supermassive black hole, but also confirmation that Einstein's theory accurately describes the behavior of matter in some of the most extreme gravitational environments in the universe. The mass measurements were staggering, about 4 million times the mass of our Sun, all contained within a region smaller than the orbit of Mercury. Nothing but a black hole could be so massive yet so compact, so gravitationally powerful yet completely dark in visible light. Sagittarius A star, as this object is now known, sits at the gravitational center of our galaxy, like a cosmic anchor point, its immense mass helping to organize the orbital motion of hundreds of billions of stars. But perhaps the most dramatic confirmation of black hole physics came with the detection of gravitational waves by the LIGO and Virgo observatories. On September 14th, 2015, these incredibly sensitive instruments recorded the characteristic chirp of space-time itself, rippling as two black holes, each containing about 30 solar masses, spiraled together and merged in a cataclysmic collision that occurred over 1 billion years ago. Picture two cosmic whirlpools, each carving its own curved depression in the fabric of space-time, gradually drawing closer together as they lose energy to gravitational wave radiation. As they approach, their orbital dance becomes faster and faster, the two event horizons racing around each other at increasing speeds until, in the final moments before merger, they're circling each other hundreds of times per second. The collision itself lasts only a fraction of a second, but it converts more than 3 solar masses of matter into pure gravitational energy, creating ripples in space-time that propagate outward at the speed of light. When these gravitational waves reached Earth after their billion-year journey through space, they stretched and compressed the 4-kilometer arms of the LIGO detectors by distances smaller than 1/10,000th the width of a proton. Yet this impossibly tiny distortion was enough to confirm one of Einstein's most profound predictions and to open an entirely new window onto the universe. In the years since that first detection, gravitational wave observatories have recorded dozens of black hole mergers, revealing a universe far more dynamic and violent than anyone had previously imagined. Each gravitational wave detection tells a story written in the language of curved space-time. The frequency and amplitude of the waves encode information about the masses and spins of the merging black holes, while the way the signal evolves over time reveals details about their final orbital dance. Some mergers involve black holes of similar mass, while others show evidence of more dramatic encounters between objects of very different sizes. The data has revealed that black hole mergers are surprisingly common, occurring perhaps once every few minutes somewhere in the observable universe. The most spectacular visual confirmation of black hole physics came in 2019 with the release of the first image from the Event Horizon Telescope, a planet-spanning array of radio telescopes working together to create an instrument with the resolution needed to directly observe the event horizon of a supermassive black hole. The target was M87 star, the black hole at the center of the elliptical galaxy M87, located about 55 million light-years away in the constellation Virgo. The image revealed exactly what Einstein's equations had predicted: a bright ring of glowing matter surrounding a dark central shadow. The shadow, about the size of our solar system when projected at M87's distance, marks the photon sphere, the region around a black hole where light can orbit in closed loops before either escaping to infinity or falling past the event horizon. The asymmetry in the brightness of the ring revealed that the black hole is rotating, with material on one side moving towards us and appearing brighter due to relativistic beaming effects, while material on the other side moves away and appears dimmer. 2 years later, the Event Horizon Telescope collaboration released an even more remarkable image, a direct picture of Sagittarius, a star, the supermassive black hole at the center of our own galaxy. Despite being much closer than M87 star, SGR-A star proved more challenging to image because its smaller mass means that matter orbits much more quickly around it, the hot gas completing a full orbit in just minutes rather than days. Creating a coherent image required sophisticated techniques to account for the rapid changes in the accretion flow during the time it took to collect the radio data. The success of the Event Horizon Telescope represents one of the greatest technical achievements in the history of astronomy. The project required coordinating observations from radio telescopes scattered across the globe, from Hawaii to Chile to the South Pole, synchronizing their clocks to within nanoseconds and combining their data to create the effective resolution of a telescope as large as the Earth itself. The result was humanity's first direct glimpse of the most extreme gravitational environment in the local universe, the edge of space-time itself. These observational triumphs have revealed that black holes are not just exotic mathematical possibilities, but common features of the cosmic landscape. Our galaxy alone likely contains millions of stellar mass black holes, the remnants of massive stars that died billions of years ago. Nearly every large galaxy appears to harbour a supermassive black hole at its centre, these cosmic giants playing crucial roles in the formation and evolution of galactic structure. The relationship between central black holes and their host galaxies has emerged as one of the most surprising discoveries in modern astronomy. The mass of a galaxy's central black hole correlates remarkably well with the mass of its central bulge of stars, suggesting a deep connection between the growth of supermassive black holes and the formation of galactic structure. How this relationship developed remains one of the great puzzles in astrophysics, but it hints that black holes may play active roles in regulating star formation and shaping the evolution of cosmic structure on the larger scales. Recent observations have also revealed that black holes aren't simply cosmic vacuum cleaners that devour everything in their vicinity. Instead, they can dramatically influence their surroundings through powerful jets of particles and radiation that extend for thousands of light years beyond the galaxy itself. These jets, powered by the rotation of the black hole and the magnetic fields threading through the accretion disk, can trigger or suppress star formation in distant regions, affecting the evolution of entire galactic neighborhoods. The study of black holes has also led to the discovery of intermediate mass black holes, objects too massive to have formed from stellar collapse, but too small to be the supermassive giants found at galactic centers. These missing links in the black hole population may form through the merger of multiple stellar mass black holes in dense star clusters, or through the direct collapse of massive gas clouds in the early universe. Recent gravitational wave detections have provided evidence for black holes in this intermediate mass range, suggesting that the universe may contain black holes spanning an enormous range of masses, from just a few times the mass of our Sun to billions of solar masses. Perhaps most remarkably, the observational study of black holes has transformed these objects from purely theoretical constructs into precise laboratories for testing fundamental physics. The motion of stars around Sagittarius, a star, has confirmed Einstein's predictions about the behavior of matter in strong gravitational fields. Gravitational wave detections have verified the existence of the ripples in space-time that Einstein predicted but never thought would be observable. The images from the Event Horizon Telescope have shown that the shadows cast by black holes match the predictions of general relativity with remarkable precision. Each new observation adds another piece to our understanding of how gravity behaves under the most extreme conditions imaginable. Black holes have evolved from being mathematical curiosities that even Einstein doubted could exist in nature to becoming some of the most precisely studied objects in the universe. They serve as cosmic laboratories where the fundamental laws of physics can be tested under conditions that can never be replicated on Earth, revealing the deep connections between matter, energy, space, and time that govern the behavior of everything from subatomic particles to the largest structures in the cosmos. As we continue to develop new observational techniques and launch more sophisticated instruments into space, our ability to study these cosmic mysteries will only improve. Future gravitational wave detectors will be sensitive enough to observe black hole mergers throughout most of the observable universe, while next-generation telescopes may be able to resolve the event horizons of black holes in nearby galaxies. Each new discovery brings us closer to understanding not just what black holes are, but what they can teach us about the fundamental nature of reality itself. In our final exploration, we'll turn to one of the most profound and unexpected discoveries about black holes, that these seemingly eternal objects are not permanent fixtures of the cosmic landscape, but slowly evaporating entities that connect gravity to quantum mechanics in ways that continue to puzzle the greatest minds in physics. Picture a perfect mirror sitting in an empty room, reflecting nothing but the faint glow of virtual particles that quantum mechanics tells us must constantly flicker in and out of existence, even in the purest vacuum. Now, imagine that this mirror is curved into the most extreme geometry possible, the event horizon of a black hole, and that its reflective properties become so warped by gravity that it begins to emit a steady stream of real particles, glowing with a temperature so faint it would take longer than the current age of the universe to boil a cup of tea. This is the essence of Hawking radiation, perhaps the most beautiful and puzzling prediction to emerge from the marriage of quantum mechanics and general relativity. The discovery of this phenomenon began not with observations through telescopes or experiments in laboratories, but with a young physicist named Stephen Hawking working alone with pencil and paper in the early 1970s. Hawking was investigating what happens when you try to apply the principles of quantum mechanics to the curved spacetime around black holes, following mathematical paths that seem to lead inexorably toward one of the most counterintuitive conclusions in the history of physics, that black holes, despite their reputation as cosmic vacuum cleaners that devour everything in their path, must actually be glowing. The mathematics that led Hawking to this conclusion are rooted in one of the strangest features of quantum mechanics, the fact that empty space isn't really empty at all. According to quantum field theory, the vacuum seethes with virtual particle pairs that spontaneously appear and disappear on timescales so brief that they normally have no measurable effect on the world around us. These quantum fluctuations represent the irreducible uncertainty that quantum mechanics imposes on our description of reality, a reminder that even nothingness has structure and dynamism when examined closely enough. Under normal circumstances, these virtual particle pairs, consisting of a particle and its corresponding antiparticle, appear together and quickly annihilate each other, returning their borrowed energy to the quantum vacuum before the universe's accounting system notices the temporary loan. But near the event horizon of a black hole, the extreme curvature of space-time disrupts this tidy process in a remarkable way. When a virtual particle pair appears just outside the horizon, the intense gravitational field can separate the two particles before they have a chance to recombine. Imagine standing at the edge of a cliff during a violent windstorm, watching leaves torn from nearby trees. Most of the time, the leaves swirl together in small whirlwinds before settling back to the ground, but occasionally, the wind is strong enough to catch one leaf and carry it over the cliff, while its partner falls back to Earth. Near a black hole's event horizon, the gravitational field plays the role of that cosmic wind, separating particle pairs with such efficiency that one member of each pair escapes to infinity, while its partner falls past the point of no return. But here's where the story takes an unexpected turn. The conservation of energy demands that these escaping particles must be paid for somehow. The universe doesn't allow something to be created from nothing, even in the quantum realm. The energy for the escaping particles comes from the black hole itself, gradually reducing its mass through a process so subtle that it makes stellar evolution look rapid by comparison. Each escaping photon carries away a tiny amount of energy, slowly draining the black hole like water seeping through an impossibly small crack in a cosmic dam. The temperature of this Hawking radiation is inversely related to the mass of the black hole. The more massive the black hole, the colder its glow. For a black hole with the mass of our Sun, the temperature would be about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that permeates all of space. Such a black hole would absorb more energy from the universe around it than it emits through Hawking radiation, causing it to grow rather than shrink in the current epoch. But as a black hole loses mass through evaporation, its temperature rises and the process begins to accelerate. The relationship is ruthlessly mathematical. Halve the black hole's mass, and its temperature doubles. This creates a runaway process where smaller black holes evaporate faster than larger ones, eventually reaching a crescendo where the final moments of evaporation release enormous amounts of energy in a brief, brilliant flash that could outshine stars. The timescales involved in this process stretch human comprehension to its limits. A black hole with the mass of our Sun would take approximately 10 to the 67th power years to evaporate completely. A span of time so vast that writing it out in ordinary notation would require more digits than there are atoms in the observable universe. During most of this impossibly long interval, the black hole would be cooling rather than warming, its Hawking radiation becoming ever fainter as the cosmic microwave background temperature drops with the expansion of the universe. Only in the far distant future, when the universe has expanded and cooled until even protons begin to decay and the stars have long since burned out, would black holes enter their final phase of evolution. In this deep future cosmos, black holes would be among the last surviving structures, glowing with their faint Hawking radiation against a backdrop of near-perfect vacuum and darkness. The largest supermassive black holes would persist for 10 to the 100 years or more, outlasting every other known form of organized matter and energy. Stephen Hawking's personal journey to this discovery carries its own kind of cosmic poetry. In 1963, at the age of 21, he was diagnosed with amyotrophic lateral sclerosis, a degenerative disease that doctors predicted would kill him within a few years. Instead of succumbing to despair, Hawking threw himself into his research with renewed intensity, making some of the most profound discoveries in theoretical physics, while his body gradually lost its ability to move and speak. His work on black hole thermodynamics began in the late 1960s and early 1970s, during the period when his disease was progressing most rapidly. The irony of this timing wasn't lost on Hawking himself. As his own physical form began to fail, he was discovering that even the most permanent-seeming objects in the universe, black holes, were subject to their own form of gradual dissolution. The mathematical elegance of black hole evaporation seemed to echo something profound about the relationship between permanence and change, between being and becoming, that transcended the specifics of any particular physical system. The discovery of Hawking radiation revealed that black holes possess thermodynamic properties remarkably similar to those of ordinary matter. They have temperatures, entropies, and heat capacities that follow precise mathematical relationships derived from their gravitational properties. The entropy of a black hole turns out to be proportional to the area of its event horizon rather than its volume, a result that seemed strange when first discovered, but has since led to profound insights about the nature of information and space-time. This area law for black hole entropy hints at something called the holographic principle, the idea that all the information contained in a volume of space can be encoded on the boundary of that volume. Just as a hologram stores three-dimensional images on a two-dimensional surface, the physics of black holes suggests that our three-dimensional reality might itself be a projection of information stored on distant two-dimensional surfaces. This principle has revolutionized theoretical physics, leading to new approaches to quantum gravity and suggesting that the apparent three-dimensionality of space might be an emergent property rather than a fundamental feature of reality. But Hawking radiation also creates one of the deepest puzzles in modern physics, the information paradox. Quantum mechanics demands that information cannot be destroyed. Every quantum state must evolve according to precise mathematical rules that preserve the total amount of information in the universe. But if black holes evaporate completely through Hawking radiation, which appears to be random thermal radiation carrying no information about what fell into the black hole, then it seems that the information contained in the original matter has been permanently destroyed. This apparent contradiction has spawned decades of theoretical investigation and heated debate among physicists. Some argue that the information is somehow encoded in subtle correlations within the Hawking radiation itself, emerging in ways so complex that they're impossible to detect with any practical measurement. Others propose that the information remains trapped at the event horizon, encoded in microscopic fluctuations of the geometry that become important only when the black hole has nearly evaporated completely. Still others suggest that the resolution requires abandoning our traditional picture of smooth event horizons in favor of firewalls, regions of intense energy that would incinerate anything approaching the black hole. In this scenario, the smooth crossing predicted by classical general relativity would be replaced by a violent encounter with quantum radiation, fundamentally changing our understanding of what happens when matter falls into a black hole. The search for a resolution to the information paradox has led to some of the most creative theoretical work in modern physics. The ADAS/CFT correspondence, discovered in the late 1990s, provides a mathematical framework where certain theories of quantum gravity are equivalent to quantum field theories living on the boundary of space-time. Within this framework, the interior of a black hole can be described entirely in terms of information stored on its boundary, potentially resolving the information paradox by showing that the information never really falls into the black hole in the first place. Recent work has focused on the concept of quantum error correction and the role of entanglement in preserving information near black holes. These investigations suggest that black holes might function as quantum computers of sorts, processing information in ways that preserve its essential content while transforming its representation beyond recognition. The emerging picture is one where black holes serve as cosmic libraries, storing information about everything they've ever encountered in forms so complex and subtle that extracting that information would require technology far beyond anything we can currently imagine. The cultural resonance of black hole evaporation extends far beyond physics into philosophy, religion, and literature. The concept of cosmic impermanence, the idea that even the most seemingly eternal objects must eventually dissolve, appears in many spiritual traditions. Buddhist philosophy speaks of anicca, the universal characteristic of impermanence that applies to all conditioned existence. The discovery that black holes slowly evaporate provides a scientific parallel to these ancient insights, suggesting that nothing in the physical universe, no matter how massive or long-lived, is immune to change and eventual dissolution. The ancient Greek concept of the Ouroboros, the serpent eating its own tail, takes on new meaning in the context of black hole evaporation. Just as the mythological serpent consumes itself in an eternal cycle of destruction and renewal, black holes slowly convert their own mass into radiation, eventually consuming themselves completely in a process that can take longer than the current age of the universe. The image captures something essential about the cyclical nature of cosmic evolution, where matter and energy flow through endless transformations without ever being truly created or destroyed. Hindu cosmology speaks of cosmic cycles where universes expand, evolve, and eventually dissolve back into the primordial state from which they emerged. The Kalpas and Pralayas, periods of creation and dissolution, span timescales that dwarf human comprehension, much like the evaporation timescales of supermassive black holes. In this cosmological framework, black hole evaporation represents a kind of localized pralaya, where organized matter returns to its most fundamental state as radiation dispersed throughout the cosmos. Modern computer simulations have allowed physicists to model the evaporation process in exquisite detail, following the quantum state of Hawking radiation as it emerges from the curved space-time around black holes. These calculations reveal intricate patterns of quantum entanglement between the escaping radiation and the black hole interior, suggesting that the information paradox might be resolved through subtle quantum correlations that preserve unitarity, the principle that quantum evolution must be reversible. The simulations also reveal that the Hawking radiation spectrum isn't perfectly thermal as originally thought, but contains tiny deviations that might encode information about the black hole's formation and contents. These deviations are extraordinarily small, corrections to the thermal spectrum that are suppressed by factors involving the black hole's enormous entropy, but they might be sufficient to ensure that information is preserved throughout the evaporation process. Some of the most exotic proposals for resolving the information paradox involve connections between distant regions of space-time through quantum entanglement. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that every pair of entangled particles is connected by a microscopic wormhole, an Einstein-Rosen bridge that links distant regions of space-time through quantum geometry. In this picture, black hole evaporation might preserve information by creating quantum wormhole connections between the escaping Hawking radiation and the black hole interior. These ideas push at the very boundaries of our understanding of space, time, and information. They suggest that the universe might be structured as a vast network of quantum entanglement, where the apparent separateness of distant regions is illusory, and information can flow through channels that exist outside our normal conception of spatial geometry. Black holes, in this view, serve as nodes in this quantum network, processing and redistributing information in ways that preserve its essential content while transforming its representation beyond recognition. The experimental detection of Hawking radiation remains one of the great challenges in physics. The radiation from any astrophysical black hole is far too faint to observe directly with current technology, overwhelmed by other sources of radiation in the universe. But physicists have created analog systems in laboratories using sound waves in fluids, light in optical materials, and ultra-cold atomic gases that mimic some aspects of black hole physics and may exhibit analog versions of Hawking radiation. These analog experiments have provided tantalizing hints that Hawking's predictions might be correct, showing thermal radiation emerging from artificial event horizons created in carefully controlled laboratory conditions. While these systems are far from perfect analogues of real black holes, they offer the possibility of testing the fundamental principles underlying Hawking radiation in experimental settings, where the relevant parameters can be precisely controlled and measured. Future space-based experiments might be sensitive enough to detect the primordial black holes that some theorists suggest could have formed in the early universe. These hypothetical objects, if they exist, would be small enough to evaporate on cosmologically reasonable timescales, potentially producing detectable bursts of high-energy radiation as they reach the final stages of evaporation. The detection of such events would provide direct confirmation of Hawking's predictions and open new windows onto the physics of quantum gravity. The study of black hole evaporation has also revealed deep connections between gravity, thermodynamics, and computation that continue to reshape our understanding of physical reality. Black holes appear to be the most efficient possible computers, processing quantum information at the maximum rate allowed by their energy and size. The holographic principle suggests that computation and information storage might be fundamental features of space-time geometry itself, with ordinary matter and energy emerging as collective excitations of underlying computational processes. These insights have led to new approaches to understanding consciousness, complexity, and emergence in physical systems. If information processing is indeed fundamental to the structure of space-time, then the emergence of complex conscious systems like living organisms might represent natural expressions of the universe's computational capacity rather than unlikely accidents in an otherwise lifeless cosmos. As we reach the end of our journey through the physics of black holes, Hawking radiation serves as a reminder that these cosmic mysteries continue to challenge and inspire our understanding of the deepest principles governing reality. The slow evaporation of black holes connects the largest and smallest scales in physics, linking the cosmic evolution of spacetime to the quantum fluctuations of the vacuum. In their patient glow, stretching across times longer than the current age of the universe, black holes remind us that even the most permanent-seeming features of reality are subject to change, transformation, and eventual dissolution into the quantum foam from which they emerged. The information paradox remains unsolved, pointing toward new physics that may revolutionize our understanding of space, time, and information itself, whether the resolution lies in firewalls, wormholes, or computational frameworks we have yet to imagine. The paradox continues to drive theoretical physics toward deeper and more unified descriptions of reality. In seeking to understand how black holes die, we may discover how the universe lives, breathes, and processes the information that gives structure and meaning to the cosmic story of which we are all part. Imagine a library so vast that its shelves extend beyond every horizon, containing not books written in familiar languages, but information encoded in the very geometry of space and time itself. The volumes in this cosmic collection are written in mathematics so fundamental that they describe not just what has happened, but what could happen, what must happen, and what can never happen within the boundaries set by physical law. The librarians of this impossible archive are black holes, cosmic entities that collect, preserve, and perhaps even process information in ways that challenge our deepest assumptions about the nature of reality itself. Throughout our gentle journey into the heart of gravitational darkness, we've discovered that black holes are far more than cosmic vacuum cleaners, mindlessly devouring everything in their path. They are elegant expressions of the universe's most fundamental principles, places where matter, energy, space, and time dance together according to mathematical rules so precise and beautiful that they seem almost too perfect to be real. Yet here they are, scattered throughout our galaxy and beyond, patient monuments to the deep order that underlies even the most extreme physical phenomena. From their violent births and the final moments of massive stellar collapse to their patient evaporation across timescales that dwarf the current age of the universe, black holes embody the full arc of cosmic evolution. They are born from the same nuclear processes that power our sun, grow through the same gravitational dynamics that organize planetary systems, and die through quantum processes that connect the largest and smallest scales of physical reality. In their existence, they bridge every major discovery in physics, from Newton's universal gravitation to Einstein's curved space-time to the quantum mechanics that governs the behavior of virtual particles in empty space. The holographic principle that emerges from black hole physics suggests something even more profound about the nature of information and reality. If all the physics occurring within a volume of space can be encoded on its boundary, then perhaps the three-dimensional world we experience is itself a kind of projection, a shadow cast by more fundamental processes occurring on distant two-dimensional surfaces. Our solid reality, with its apparent depth and substance, might be no more fundamental than the flickering images on a movie screen, real in our experience, but ultimately emerging from something far more abstract and mathematical. This possibility doesn't diminish the importance or meaning of our everyday experience, but it does suggest that reality operates on levels of description that extend far beyond what our senses can directly perceive. Just as we've learned that solid matter is mostly empty space punctuated by tiny atomic nuclei, and that those nuclei are themselves composed of even more fundamental particles, the holographic principle hints that our three-dimensional experience might be an emergent property of something even more basic and beautiful. Black holes serve as natural laboratories where these ideas can be tested and refined. Their event horizons provide the clearest examples we know of holographic surfaces, two-dimensional boundaries that somehow encode all the information about the three-dimensional regions they enclose. The mathematics that describe how information is stored and processed near these boundaries may eventually lead to a complete theory of quantum gravity, a unified description of how space, time, matter, and energy behave under all possible conditions. The information paradox continues to challenge our understanding, pointing toward revolutions in physics that may be as profound as the discoveries of relativity and quantum mechanics. Whether the resolution involves firewalls, wormholes, quantum error correction, or conceptual frameworks we haven't yet imagined, the paradox serves as a beacon guiding theoretical physics toward deeper truths about the nature of information, causality, and existence itself. Perhaps most remarkably, black holes have taught us that the universe has a sense of cosmic justice. Even these most extreme manifestations of gravitational power are subject to their own form of mortality through Hawking radiation. The same quantum processes that govern the behavior of atoms and molecules ensure that no black hole, no matter how massive, can persist forever. They must eventually return their contents to the cosmos in the form of radiation so faint and subtle that detecting it pushes the boundaries of what might ever be experimentally accessible. This slow evaporation connects black holes to the broader story of cosmic evolution, the gradual transformation of matter and energy through cycles of concentration and dispersal that have been operating since the Big Bang. Stars gather diffuse hydrogen and helium into dense nuclear furnaces. fusing light elements into heavier ones before dispersing those products back into space through stellar winds and supernova explosions. Galaxies collect this enriched material into new generations of stars and planets, creating the chemical complexity that makes life possible. Black holes participate in this cosmic recycling on the longest possible timescales, slowly converting organized matter back into pure radiation that will eventually thermalize with a cosmic microwave background. In the far future, when all the stars are burned out and the universe has expanded and cooled until even protons decay, black holes will be among the last organized structures, glowing with their faint Hawking radiation against a backdrop of near-perfect vacuum and darkness. The privilege of living during the era of gravitational wave astronomy cannot be overstated. For the first time in human history, we can listen to the universe in a completely new way, detecting the ripples in space-time itself as black holes merge and spiral together in cosmic collisions that occurred billions of years ago. Each gravitational wave detection is like receiving a message written in the fundamental language of geometry, telling us stories about the most extreme events in cosmic history through direct measurements of the fabric of reality itself. The images from the Event Horizon Telescope have given us our first direct glimpses of the edge of space-time, showing us the shadows cast by event horizons against the brilliant glow of superheated matter. These photographs represent one of the greatest technical achievements in the history of astronomy, requiring the coordination of telescopes across the entire Earth to create instruments with the resolution needed to resolve features smaller than our solar system at distances of millions of light years. Future observations will undoubtedly reveal new surprises about black hole physics. Space-based gravitational wave detectors will be sensitive enough to observe black hole mergers throughout most of the observable universe, revealing the cosmic history of these objects from the early universe to the present day. Next-generation telescopes may be able to resolve the event horizons of black holes in nearby galaxies, testing our theories of gravity and space-time under conditions that approach the theoretical limits of what's physically possible. The search for quantum gravity, a theory that can describe how gravity behaves when quantum effects become important, continues to be driven largely by the puzzles that black holes present. The marriage of general relativity with quantum mechanics that's required to understand Hawking radiation has already led to insights about the nature of space-time that may ultimately revolutionize our understanding of reality itself. The information paradox, the holographic principle, and the connections between geometry and quantum entanglement all point toward a future physics that may be as different from our current understanding as quantum mechanics was from classical physics. These developments remind us that science is not a collection of final answers, but an ongoing conversation between human curiosity and the deep patterns that govern the cosmos. Each new discovery opens up new questions, new puzzles, new opportunities to push the boundaries of understanding. Black holes, which began as mathematical curiosities in Einstein's equations, have become windows into some of the most profound questions we can ask about the nature of existence. The fact that these objects exist at all still feels almost miraculous. The precise balance of physical constants that allows matter to collapse beyond the neutron star stage while still permitting the formation of stable atoms and molecules seems finely tuned in ways that continue to puzzle cosmologists and philosophers. If gravity were slightly weaker, black holes might never form. If it were slightly stronger, the universe might collapse back on itself before stars and galaxies could evolve. The existence of black holes is intimately connected to the existence of everything else we observe, part of a cosmic web of relationships that extends from the smallest quantum scales to the largest structures in the observable universe. This interconnectedness suggests that black holes are not isolated phenomena, but integral parts of a larger story about how complexity and organization emerge from fundamental simplicity. The same principles that govern the formation of black holes also govern the formation of stars, planets, and ultimately the chemical and biological processes that lead to the emergence of life and consciousness. In studying these cosmic extremes, we're exploring the conditions that made our own existence possible. Standing under a starry sky, you might now look up with a different kind of awareness. Somewhere among those points of light are massive stars in the final stages of their evolution, perhaps only days or hours away from the core collapse that will create new black holes. The darkness between the stars, which seems empty to our eyes, may already contain millions of these invisible monuments to stellar death, each one carrying the compressed history of a massive star's entire lifetime within its event horizon. The gravitational waves from black hole mergers are passing through your body at this very moment, ripples in space-time so faint that they stretch and compress you by distances smaller than a fraction of the width of an atomic nucleus. These cosmic messengers have travelled for billions of years to reach us, carrying information about events so extreme that they convert significant fractions of stellar masses into pure gravitational energy in fractions of a second. In contemplating black holes, we encounter the universe at its most extreme and its most elegant. These objects represent the ultimate triumph of gravity over all other forces, yet they do so in ways that reveal the deep unity underlying all physical phenomena. The same equations that describe the gentle bending of light around the sun also describe the violent dynamics of matter falling through event horizons. The quantum mechanics that governs the behavior of atoms in our bodies also determines the slow evaporation of supermassive black holes through Hawking radiation. Perhaps most importantly, black holes remind us that the universe still holds profound mysteries at the very foundations of physical reality. The information paradox, the nature of singularities, the relationship between quantum mechanics and gravity. These are not merely technical problems for theoretical physicists to solve, but fundamental questions about the nature of existence that touch on the deepest philosophical and scientific puzzles we can pose. The search for answers continues to drive physics toward new conceptual frameworks and mathematical tools that may eventually provide a complete description of how reality works at all scales. Whether that ultimate theory involves strings vibrating in 11 dimensions, discrete elements of space-time geometry, or computational processes more fundamental than matter and energy, the path towards such understanding runs directly through the event horizons of black holes. As you drift towards sleep, perhaps you can carry with you this sense of connection to the cosmic story that black holes help to tell. These invisible lighthouses scattered throughout the universe mark places where matter and energy have pushed the boundaries of physical law to their breaking point, revealing glimpses of the mathematical poetry that underlies all of existence. In their patient glow, too faint to see but too profound to ignore, they remind us that even in the deepest darkness, the universe continues to follow rules of exquisite beauty and precision. The cosmic library hypothesis suggests that all of this information, every particle that has ever crossed an event horizon, every detail of every stellar collapse, every quantum fluctuation that has contributed to the slow evaporation process, is somehow preserved in the holographic encoding of space and time itself. If this is true, then black holes are not cosmic graveyards where information goes to die, but cosmic archives where the universe stores the memory of its own evolution. In this grand library of space-time geometry, Every black hole is both a collection and a catalogue, preserving not just the matter and energy that formed it, but also the story of how that matter and energy came to be concentrated in one place and time. The mathematics that describe these processes are the same mathematics that describe the formation of galaxies, the evolution of stars, the chemistry of planets, and ultimately the emergence of complexity, life, and consciousness. The black holes keep their vigil through the cosmic night, patient guardians of information and entropy, slowly returning their contents to the universe through processes so subtle they make the formation of stars look sudden. In their silent existence, they remind us that we are part of a story larger and more beautiful than we can fully comprehend. A story written in the language of curved space-time, told through the patient evaporation of invisible monuments to the creative power of gravity itself. This is the Sleepy Astronomer, wishing you peaceful dreams filled with wonder, and thanking you for joining me on this gentle journey to the very edge of space-time itself. Until we meet again among the stars, sleep well, and remember that even in the deepest cosmic darkness, the universe continues to unfold according to principles of extraordinary beauty and grace.